Okay, folks, here we are with the very last section of Chapter 2, where we're going to be talking about nearest neighbor methods for estimating probability distributions in a non-parametric way. So let's see what that's about. Okay, so remember we were just talking about these kernel methods, right? So remember these methods that, you have a data point here, and what it does is it estimates the probability by, putting a little kernel over it, and then you add up all the kernels, and you hope that you can find a good kernel size that matches the shape of your distribution. And so there's this issue of picking the right kernel size, but there's a second issue of, well, why have just one kernel size? Why, maybe for example, the data in this region seems actually quite sparse, so maybe you should have kind of a wider distribution, a larger kernel there. Whereas over here, it seems to be a lot of data. Maybe you want to have kind of a narrower kernel, or something like that. So is it possible to, I mean, certainly it's possible, but can we come up with kind of a good way of adjusting the kernel size to the data? And so that's what one of the things that these nearest neighbor methods do. So he says, one of the difficulties of the kernel approach to density estimation is that the parameter h, which we're talking about, governing the kernel width, is fixed for all kernels. In regions of high data density, a large value of h may lead to over-smoothing. So if you've got kind of a very broad kernel and there's lots of data points, you can resolve some, you might be able to resolve some, fine fluctuations. If you have a big kernel, you'll just kind of smooth over that. And a washing out of structure that might otherwise be extracted from the data. And reducing age may lead to noisy estimates elsewhere in the data space where the density is smaller, right? So you can kind of, maybe you can, try to use a very narrow estimate, but then you start in these regions where there isn't enough data, you start putting in like zero probabilities here. And maybe it's actually not a zero probability. And we find that in fact the probability is small, but it's not actually quite zero. So this might be too fine of a kernel to use over here. Whereas, so you might want to use something smoother, like something of this size, but that might be then too broad. It might wash out, as it kind of indeed does when you have lots of data. Okay, so thus the optimal choice for h may be dependent on location within the data space. So this issue is addressed by nearest neighbor methods for density estimation. Okay, so then he says we return to our general result 2.246. So this was this cool. I like the way he split it up, the kernel methods and the nearest neighbor methods. It's a nice way of organizing the two. And remember, the idea there was that we said that the probability, I guess it was like, yeah, in around some region x, and we put kind of a volume around it, and this was equal to the number of data points we had in that region x divided by our total number of data points, so the fraction of data points, and then because it's a probability density we're after, there's a volume there. And remember, this was coming from this idea that px in the volume, kind of the probability itself, not the probability density, should equal to the fraction of points you have inside that volume. And now the point was that with the kernel methods, what we did was, as he pointed out, we kind of fixed the volume. So we had kind of this fixed size, and then we just go around counting k. So n is fixed, k and v are the things that can vary. And so what with the kernel methods, we would keep the volume the same. So we would just kind of take this little volume all over the space and count how many points fall into it. And sometimes, for example, here, we would get settings where the volume would be too small. You would get these like zero probabilities showing up, which might not actually accurately reflect what's going on in the data. So the other approach, which we're obviously talking about now, is to actually adjust, to hold k fixed and adjust v, so expand the volume to always get a certain number of data points showing up, and then you can compute the probability that way. So that's what these nearest neighbor methods are about. Okay, and so instead of fixing v and determining the value of k from data, we consider the fixed value of k. I should actually, I think, underline this, a fixed value of k, and use the data to find an appropriate value of v. So k is fixed, v is going to expand or contract. To do this, we consider a small sphere centered on the point x at which we wish to estimate the density p of x, and we allow the radius of the sphere to grow until it contains precisely k data points. The estimate of p of x is then given by 2.246 with v set to the volume. I should highlight all this. The estimate is then with v set to the volume of the resulting sphere, and this is the k nearest neighbors. And he's got a couple of figures, so we'll come to these first, but it's actually, I wanted to switch to a different book for a moment, because it's got a kind of a slightly nicer pictures for this thing. So let's go to this one, this book, Pattern Classification by Duda and Stark. I think it still is a classic, I think, and it was the classic, I believe, before Bishop came out. So worth knowing about, but there's actually nice pictures of what this actually looks like. So let's just zoom in here and see how it would work. So here he's shown the kernel, the resulting estimates for a kernel of size 3 and a kernel of size 5. But let's just first start with the kernel of size 1. And here are the actual data points. And you'll just get a sense of kind of what it looks like, right? So the idea is let's try coming in from all the way over here. Okay, so the idea is we're trying to figure out, what is the probability at this point. So essentially we say, and we're going to consider the k equals 1 case. Oops, you guys can't see, so let me, there we go. So this is the k equals 1 case. Okay, so what are we doing? We're going to be looking for, so in that case, p of x is equal to 1 over times the volume to get one data point in. And so, well, what's that volume? Well, if you're already, it's in one dimension, the volume is going to be a length. So this is going to equal to 1 over n times x minus, I'm going to call it x hat, where x hat is the nearest data point, right? Because that's the smallest expansion you have to do. And this x hat should be a function of x, actually, right? This will be x hat as a function of x. So that'll be the nearest point in the data to the point you're interested in. So let's see how that behaves, right? So this is going to be, so this is a volume element, right? This is v. Okay, so if we're all the way out here, well, where is the nearest point? Well, it's quite a ways out there, right? But as we get closer, this distance here is going to shrink. So we're going to get kind of 1 over d behavior. So it's going to look kind of something like this. It actually kind of makes sense. When we arrive at that point, it's going to diverge completely. So we're going to get something that kind of looks like, doesn't quite go to 0, right? It just has this kind of, 1 over, d behavior as you go to negative infinity. Okay, so then so it diverges there, and we're going to call this as k equals 1. You guys can see that. Then as you pass the point, then it's going to kind of start coming down again until all of a sudden you start becoming closer to the second data point, in which case it'll start going up again, and it'll kind of diverge there, it'll have this kind of funny look, so etc. And then at the end it'll kind of start diverging with 1 over d again. When you have 3 data points, it's kind of you get kind of a slightly smoother case, right? Because so when you're far away, it'll still have this 1 over d behavior, because essentially all your data points will be at relative to the distance that your point of interest is. Your entire data set is actually just one location. So it'll almost be like you have one single data point. As you get closer, you start getting a little bit of a kind of a smoother result, right? Because let's say, I'm going to change colors now. So let's say I'm over here. So what's my volume? Well, it's going to be the distance to the nearest 3 data points, right? Which is this distance. So as it will kind of keep going up. It will keep going up. And then, so this distance is now going up, going up, going up. I don't know, something like that. He's actually got it here. And then the distances start getting larger again, because now you're kind of arriving in, now this gap starts becoming important. So the volume is expanding again. Here you see that the volume at this location is kind of about as tight as it can be. As you start going farther out, I guess past the center of mass of this collection, past their mean, it will start going back down. But then all of a sudden, a new data point will kind of start showing up, and you start getting this. So you never get this. You don't get this divergence behavior. You get kind of a slightly smoother effect happening, and it keeps going. With 5, it's the same thing. You can imagine if you had, if your k was equal to your entire data set, then you would get kind of the maximum smoothness, right? So it would just, it would just be kind of a very, and we'll see something like that in his figures. So hopefully that kind of gave you a little bit of a sense of how these things are computed. Let's go back to Bishop. Basically, here's a situation when k is equal to 1. So exactly as we discussed, so at the data points, you get these big divergences. You get 1 over x behavior between the points, etc. And as the number of points that you use increases, you get kind of a smoother estimate, because you're now no longer dependent on the position of exactly one data point. As one data point drops out, maybe another one will shortly thereafter come in, etc. So the volumes aren't so sensitive to each point, so you get a smoother estimate. Okay, so that's kind of the nearest neighbor approach. We see that the value of k now governs the degree of smoothing, and again, there's an optimum choice for k that is neither too large nor too small. And note, and this is the thing, to note that the model produced by k nearest neighbors is not a true density model, because the integral over all space diverges. And so there's an exercise on this, it's a simple exercise to show why this is the case. And it's basically just to kind of give you kind of a decisive hint. So you'll have, your P of x is going to be, k over nv, right? And k and n are fixed. And so this is going to be just, and v is going to be a function of x. So if we want to integrate P of x dx, this is going to equal to, it's going to be proportional, k over n times the integral of 1 over v of x dx, right? And now 1 over, if you're kind of far away from, and this is going to be from, minus infinity to infinity. If you're doing kind of some kind of polar coordinates, you can imagine you're kind of very far from your data points. You still have to integrate over the rest of space. So your data points are kind of collapsed to a single point effectively because you're so far away. And that single point is sitting at the origin. So effectively, you're kind of integrating a sphere from some radius out to infinity. You're integrating this function kind of spherically, that's what I mean. So now this is going to be, if we do it in, let's call it r0 to infinity. And now the v of x is going to be proportional to, so we'll just, r to your dimensions. And your d of x going in those shells is going to be r d minus 1 dr, right? So this is going to be r naught infinity 1 over r up to proportionality dr, which is going to be ln r infinity r naught, and this infinity thing is going to kill you. So it's basically, it's just this effect, the fact that the probability doesn't go to 0. I know you're integrating it over infinity, so that's going to blow up. So that's why it's not a true density. Now, interestingly, in the other book, it mentions that this is actually not necessarily problematic. It doesn't go into much detail, but it says the fact that we don't get these 0 probabilities can be helpful in high dimensions. He doesn't say why. So I'm just going to put that out there. I think maybe, it could be because, so in some settings, inference settings, like you don't want to have kind of 0 probability, right? Like chances are it's not that the probability is 0 of observing a particular set of features. It's just that you don't have enough data. So this might be kind of a natural way of just kind of being a little bit more conservative and being like, well, actually, just because we haven't observed something in high dimensions, we'll never observe nearly everything. So it might be kind of a good way of just keeping the probabilities non-zero. But that's just me kind of guessing what it could be about. Okay, and then finally, he said, so we're going to kind of use this for classification, and we're going to come up with this cool nearest neighbors rule. So we close this chapter by showing how the k nearest neighbor technique for density estimation can be extended to problems of classification. Okay, so to do this, we apply the k nearest neighbor density estimation technique to each class separately, and then make use of Bayes' theorem. So essentially, the game is going to be to figure out the probability of each class given your data point, and then pick the class which has the highest probability for that data point. Okay, so let's suppose we have a data set comprising nk points in class ck with n points in total. So they all sum up properly. If we wish to classify a new point x, we draw a sphere centered on x containing precisely k points. So we find the k points nearby, irrespective of their class. So just whatever the k points are, that's the whole point, right? We're going to find out, like, locally, what is the distribution of data that we have. Now, suppose the sphere has volume V and contains k sub k points from class C. I mean, he could have used a different letter, I think. Providing, then 2.246, this famous formula, this one right here, provides an estimate of the density associated with each class. So now notice what you're doing here. You're saying the probability of you just kind of filter. You say the likelihood of this class, or the probability of the data point given this class, is going to be proportional to the number of points, the fraction of, this will be the number of points in that class divided by, the number of points in that class in that volume divided by the total number of points in that class. So effectively, you're just estimating a bunch of different probabilities for each of the different classes. So those are the kind of the class likelihoods. So you say, what is, if you're coming from class CK, what's the probability of this particular point? Well, then you just limit yourself to the data points that are coming from that class, hence the sub k's, and you compute this thing. Okay, so that's the likelihood. Similarly, the conditional density is given by, so this is just the overall, you can sum this over, this is just the probability of the total density, basically, so that the unconditional density. And the class priors are just the fraction of the points coming from each class divided by the total number of points. So this kind of makes sense. All right, so now we have all the pieces we need to use Bayes' theorem, and we plug all these things in, and we get that the posterior probability of a class at a particular point is, somewhat intuitively, the number of points in that class divided by the total number of neighbors we're choosing. So it kind of makes kind of intuitive sense, right? You can say the probability of a particular class at a location is just a fraction of the neighbors that belong to that class. So that's pretty cool. And we can see, so again in the PDF, it doesn't have this figure is kind of incomplete, so that's why I've kind of taken a picture from the book and pasted it here. Okay, so if we wish to minimize the probability of misclassification, this is done by assigning the test point x to the class having the largest posterior probability, corresponding to the largest value of k sub k divided by k. So this was, remember, if you go back to, I think it was chapter 1, when we were looking at Bayesian decision theory, and we were in a situation where all incorrect decisions were equally bad, then the thing you want to do is just assign to the class with the highest probability, largest posterior probability. So that's what we've got. So essentially, thus to classify a new point, we identify the k nearest neighbors from the training data set, and then assign the new point to the class having the largest number of representatives among this set. Okay, so this is, we probably heard of this as the nearest neighbor, k nearest neighbors, or the nearest neighbor rule in case k is equal to 1. So let's kind of have a look at what that looks like. Again, I had to kind of paste these pictures in. Okay. So here is a kind of a point of interest, and we're saying, well, what class are we going to assign it to? In this case, k equals 3 here. And so we look at its 3 nearest neighbors, and it looks like 2 of them are red, 1 of them is blue, so you assign it to red. And if there's a tie, you can just assign them at random. But when your k is odd, then there'll never be a tie. If you have 2 classes at least. Okay, now here's a situation where k is equal to 1. Oops. Oh. That's a bit annoying. Okay, here is k equals to 1, and when k is equal to 1, well then you get these interesting things happening where the decision boundaries are hyperplanes that are kind of perpendicular to the line between kind of two points of a different color. Because essentially you're saying this is, if these 2 points were the only ones present, then the line separating the 2 classes would be a line of points that are equally distant between those 2, right? So in that setting, that would be the dividing line. But now, because there are other points, well, then you kind of get an intersection of those things happening. So for example, once you're over here, then now the closest point that will kind of decide whether it's something red or blue is actually this one. So now you get a different dividing line. But these dividing lines will, in the k equals 1 case, will always be perpendicular to a line separating, to the line between 2 points of a different color. So that's pretty cool. And that's kind of what the decision boundary would look like in the k equals 1 case. Yeah. The ties can be broken at random. In particular case, k equals 1 is called the nearest neighbor rule because the test point is simply assigned to the same class as the nearest point from the training set. And that's in the figure. Okay, and now he's just applied it to kind of a real world data set. So to the oil flow data into chapter 1 for various values of k. So let's have a look at that. So again, so these are the points have been labeled by the 3 different classes they're in. And again, here is the k equals 1k. So what you're doing here is you're just taking for every single one of these points, you're just looking at it and saying, is my nearest point data set point, what color is it basically? And for all of these points, the nearest data set point is blue, and including these guys down here. But then over here, you've got this island of green, this peninsula of green actually, controlling a little area. And then you've got these little bits of red happening. But you can see like there's like a lot of, perhaps a lot of noise there. Maybe like, is it really the case that the data, has a little island of green there? Like probably not. So here's what it looks like when k is equal to 3. And now you can see that these little islands of green are kind of getting outvoted. So now you get this big chunk of, of red being classified. And, this isolated green point, well, it's kind of getting, ruled out. And as you increase k, then these regions become maybe a little bit smoother to some extent. I wouldn't necessarily call this smooth, but you know what I mean. You can kind of smooth over the data a bit more, so you get these bands rather than these, crazy, crazy jaggedy shapes. So it's kind of it's a smoothing parameter. Okay. Okay. Yeah. So that small k produces many small regions of each class, whereas large k leads to fewer larger regions. Okay. An interesting property of the nearest neighbor k equals 1 classifier is that in the limit of n to infinity, the error rate is never more than twice the minimum achievable error rate of an optimal classifier. That's a cool result. I think I've come across it before, but can't give you any intuition for it. So just have a look at that. Have a look at that paper. Might be a fun one. Maybe if it's not too hard, it might be a fun one to do together. Okay. So yeah, good to know. As discussed so far, both the k-nearest-neighbor method and the kernel density estimate require the entire training set to be stored, leading to expensive computation as the data set is large, right? So for example, for the nearest neighbor stuff we're doing, you need to know the neighbors, and and every time you're computing a particular probability, you need to look at your training set again. And if your training set is large, that's going to be really prohibitive. This effect can be offset at the expense of some additional one-off computation by constructing tree-based search structures to allow approximate near neighbors to be found efficiently without doing an exhaustive search on the dataset. Okay, so that seems like a solution. But then he says these non-parametric methods are still severely limited. So I wish he would say a bit more about this, because it's not clear why. At least, it'd be nice to kind of go a bit into that. I mean, okay, so we saw the nearest neighbor. It's not really a probability. Yeah, maybe, okay, you have to store the data set, but there are ways around that. So I wish he'd kind of gone into this a bit more. On the other hand, we have seen that simple parametric models, which we've been talking about in the rest of the chapter, are very restricted in terms of the forms of distributions they can represent. So we therefore need to find density models that are very flexible, and yet for which the complexity of the models can be controlled independently of the size of the training set. And we're going to see how to do this. So basically, stay tuned. Maybe there'll be a kind of a good middle ground between these two situations. Awesome. So as you can see, we're kind of coming up to the exercises. So that means we are at the end of the chapter. So I think I will do, in the next video, I will do kind of a chapter recap. And then it'll be on to chapter 3. So I hope you guys have learned some stuff. Please let me know if you have or you haven't in the comments. And I look forward to seeing you in the next video. Thanks.